thanks. It's great to be back here in a much better. Last time I was debating some New Age philosopher in this very room, and this is so much more fun. It's great to be with my colleague Paul Davies. And the good thing is that I've been given the easy job, which is the origin of the universe, and Paul has to talk about the origin of life, which is much more complicated. And so let's see. We'll also see if the technology works. So I'm going to try and see if my remote works. Yes, there we go. I just want to say it's a beautiful day, and I just flew in for a busy week here in Australia. And the great thing about cosmology is it takes us away from the myopia, the worries about everyday life. So the story I want to tell is, right now we're living in the best of times, and by the best of times I mean that the Large Hadron Collider is turned on again in Geneva. It hasn't created a black hole that's destroyed the world, and that's even better. And at the same time we're in the worst of times. I couldn't resist. Sorry, I couldn't resist. Sorry, I'm going to be on Q&A tomorrow when I'm getting in the mood. But the great thing is we don't have to worry about this too shall pass. And so I want to talk about really important stuff like the universe. And this is a recent Hubble Space Telescope picture, a multi-color image, actually the most recent deep space image. And except for that one spot right there, which is a star, every dot in this picture is a galaxy. And these galaxies are in real colors, and the blue galaxies, the really distant ones, the faint ones, are maybe 9 or 10 billion light years away. So the light from them left 9 or 10 billion years ago, well before our sun formed 4.5 billion years ago. And it's interesting to me, whenever I see an image like this, it takes me a lot of places. For example, many of the stars in this image last 5 to 10 billion years, and that means most of the stars in this picture don't exist anymore. Okay, and just like if they took a picture of us today, by the time it arrived on the astronomers on any star system that would then form in these systems, our Earth would be gone, because in 4 or 5 billion years it would be toast, literally. And so pictures like this inspire us to think about the most fundamental questions, and some of which we're going to talk about today, the origin of the universe. And now when we look back with telescopes, we can see back pretty far, but we can't see all the way to the beginning. Now, the fact that there is a beginning is important, because that's also relatively recent. In 100 years ago, the conventional wisdom was that the universe was static and eternal. And all of that changed because of a guy who's one of my heroes, Edwin Hubble. And he's one of my heroes because he's given me great hope for humanity, because he began life as a lawyer and then became an astronomer. But anyway, he discovered many things, and I don't have time to talk about all of them, but the prime thing he discovered was that the universe isn't static, that the universe is actually expanding. And so I just was asked again by email today the same question, so I want to explain the expansion that he saw. So let's see if, there we go. So briefly, this is not the biological part of the program. See, these are not sperm, these are galaxies. But if we're here in our galaxy, what Hubble discovered was that if you look out at distant galaxies, on average, they're all moving away from us. And the farther they are away from us, the faster they're moving away. And those that are twice as far away are moving twice as fast. Those that are 3 times as far away are moving 3 times as fast, etc. So when you see this, it's obvious what's happening. We are the center of the universe. And it's not the case, so, as my friends remind me on a daily basis. But there are lots of ways to try and think about this, and it's hard to see why this would mean that we're not the center of the universe. So I want to explain it by going to another universe, one that I can create on a frame like this. So here's a 2-dimensional universe with a segment of galaxies, and another later on. If you're standing outside this 2-dimensional universe, you can see these galaxies, and it's bigger. So you can see that the whole thing's expanding. But what would you see if you were sitting on one of these galaxies? So pick one. Pick that galaxy there. Well, we can see what you'd see if you were sitting on that galaxy by superimposing this picture on top of this one, placing that galaxy on top of itself. And what do? You see everything's moving away from you. And those things that are twice as far away have moved twice the distance in the same time. Those that are 3 times as far away, 3 times the distance, etc. And it doesn't matter what galaxy you pick. You see the same thing from every galaxy. And so really what that means is when you see something like this, it's really semantics. Either every place is the center of the universe or no place is the center of the universe. It doesn't matter. But what Hubble discovered told us that the universe is expanding. And that means, of course, that we can work backwards, and that means it had a beginning, because it's expanding at one point, which we now understand is 13.8 billion years ago, approximately. Everything, all 100 billion galaxies in the observable universe, each containing 100 billion stars or so, all of that was contained originally in a region smaller than the size of a single atom. And it's amazing to think of that being possible, and that people like me get paid to even worry about it, or we can talk about it with a straight face. But as I'm going to talk to you today about, we're at the threshold, potentially, of directly being able to measure the universe up to a billionth of a billionth of a billionth of a billionth of a second after the Big Bang. And that is something I never dreamed of in my lifetime originally, although I actually proposed it, but I forgot about it. So, by the way, this is Hubble's image of the expanding universe from 1929. This is distance and velocity, and you can see he was a great scientist because he knew to draw a straight line through his data set. But with no reason for it. But you could see that that's that rough image. But it was very difficult back then, and because, in fact, to measure the expansion of the universe, you have to measure both the velocity of objects away from us and the distance away from us. And it's gotten harder because it's gotten easier, I should say. It was hard then because when you're trying to measure the expansion rate, how do you know the distance of distant objects? How do you know how far away they are? We don't have rulers that'll measure that distance. So you have to use what we call a standard candle. Namely, you have to look at something, say a 100-watt light bulb. If I had a 100-watt light bulb in the back of the room, I could tell how far away it was by just having a light meter here and seeing how much power was received by my light meter and knowing that the light spreads out in a certain way. But of course, the universe isn't populated by 100-watt light bulbs, and so we have to look for objects that we think are standard candles, and this was a problem for Hubble. He actually got the answer wrong by a factor of 10, which observational astrophysicists have attempted to emulate ever since. And the reason he got it wrong is that he had a hard standard candle. Actually caused a problem because the expansion rate that he measured would have made the universe 1.5 billion years old. And this is in 1929, and we already knew, except in a bunch of American states and probably Queensland, that the universe that the Earth is a lot older than that. So it was embarrassing to have the universe be younger than the Earth. But he got it wrong, and it's really closer to 14 billion years. And I think I have an image of the best standard candle we now have, which has got an Australian bit of content to it. This is a galaxy not too far away, not too long ago. It's only about 70 million light years away, a spiral galaxy like our own. And you can see this star shining with the brightness of 10 billion stars. That's how many stars are on the center of this galaxy. How can it shine with the brightness of 10 billion stars? It's a supernova. It's a star that's just exploded. The brightest fireworks in the universe. And I've talked about in other lectures how important supernovae are for us because every atom in your body came from one. At least every atom in your body has experienced the most violent explosion in nature several times because in the Big Bang, only hydrogen and helium were produced. But the important stuff for you, the carbon, the nitrogen, and the oxygen, all of that was only produced in the fiery cores in the center of stars. And the only way they could get into your bodies is if the stars were kind enough to explode. And it's weird to think that every atom in your body is literally stardust. It's experienced the most violent explosions in nature. But it turns out these supernovae, this particular type of supernova, is a wonderful standard candle, as my good friend Brian Schmidt at Australian National University realized. And he and colleagues used it to try and measure the expansion of the universe over long times, and going back as far as he could, because they're so bright you could see them across the other end of the universe. And he was trying to measure the rate at which the universe was slowing down. And to his surprise, he discovered something else, which was very good for him. This is the Hubble diagram. This is the most complicated picture I'm going to show, so it's all downhill after this, so relax. So this is like the Hubble plot from before with velocity versus distance. And everyone had expected for very distant objects for these curves to sort of bend down. So the way to see this is to draw a straight line through this data set and make it all horizontal. And these are distant supernovae that he and another team were measuring. And everyone had expected these supernovae to lie along this curve to measure the rate at which the universe is slowing down. Because of course the universe is slowing down because gravity is attractive. And therefore it should slow the expansion of the universe. And by measuring the rate at which it was slowing down, you could determine how much matter there was. But what was discovered was that these distant supernovae didn't lie below the straight line or even on the straight line. They lay above the straight line. Now there's two explanations to this. One, the data is wrong, which it usually is in physics and cosmology the first time around. Or two, the expansion of the universe is actually speeding up, getting faster and faster. And the only way that could happen is if you actually put energy in empty space. Because while all of you have taken physics know gravity sucks, it always pulls, it never pushes. If you put energy in empty space, it's actually repulsive. It's gravitationally repulsive. And therefore, if the universe is expanding ever faster, it means most of the energy of the universe resides in empty space. That means if you take a region of space and get rid of all the particles and the radiation, so there's nothing there, it still weighs something. And we don't understand why. It's the biggest mystery in science. I mean, I'd actually proposed it a few years ago, but I didn't believe it was really true. I was just being heretical. But it's true. And what Brian discovered, of course, was this big mystery, and for that he won the Nobel Prize with several other colleagues. But that means that's part of something that I want to stress in the next few minutes, which is this relationship between the biggest stuff in the universe and the smallest stuff in the universe. Because you can ask, how could empty space have energy? And the answer is, well, before I do that, this is one of my favorite images that I got from a colleague of mine. This has been in many different cultures over the last 3,000 or 4,000 years. It's called an Ouroboros. Normally called a snake that eats its own tail, although this particular snake has legs. But that's an evolution issue, so Paul can talk about that. But the thing about the universe is, because it's expanding, if we want to understand the very biggest structures we see, we really want to understand the very smallest structures we can see, because we can talk about humans and stars and galaxies and clusters of galaxies, but once we get to the very biggest scales, because the universe is expanding and because it was all once contained in a region smaller than the size of an atom, the initial conditions that determined the largest structures we see today, including our galaxies and our very existence, were determined by physics at the very, very smallest scales, particle physics. So there's that symbiotic relationship. And in fact, the discovery of dark energy, as it's called, is one example. Because when we talk about empty space, when we think about physics on the smallest scales, where we need to use quantum mechanics as well as relativity, empty space is not what we thought it was. Empty space is a boiling, bubbling brew of virtual particles. This is actual calculation of what the space inside of a proton looks like. It was shown at the Nobel Prize ceremonies by the people who actually were able to do the calculation. But if you went to a good school, and this is Australia, so hopefully many of you did, you learned that a proton is made of 3 quarks. I can see, how many people heard that? 5 or 10? No, actually a few more. Well, we lie to you. Most of the mass of a proton comes from virtual fields, because when you put quantum mechanics and relativity together, space is really a boiling, bubbling brew of virtual particles popping in and out of existence in a time scale so short you can't even see them. So they're called virtual particles. So empty space isn't really empty, although there's nothing there. There's virtual particles popping in and out of existence. That sounds like philosophy, like counting angels on the head of a pin. But these virtual particles, while you can't see them directly, can have indirect effects. And one of them is to produce most of the mass of the proton. We can actually do the calculation. If you don't include the effect of virtual particles, you get the wrong mass by a factor of 10 for the mass of the proton. If you include these virtual particles and fields, you can get the mass of the proton. So it's possible that quantum processes at very small scales can give energies to things. And therefore you think, well, maybe quantum processes give an energy to empty space. And we can understand this energy that we see in the universe. The problem is when we do the calculation, we come up with the worst prediction in all of physics. We come up with a number which is 120 orders of magnitude too large, which is a big mistake. And no, I have a bunch of jokes there, but I'm not going to use them. But that means there's something fundamental we don't understand about the energy of empty space, and probably something that probably involves understanding the quantum theory of gravity. And that really probably means that if we want to go back to the very beginning of time, we have to have a theory. But to have theories, we have to have observations. And so this problem, though, illustrates the fact that we really want to. There are other reasons to go back to the origin of the universe, to the earliest moments of the Big Bang, not just because we'll be able to understand galaxies and clusters of galaxies, but because we'll be ultimately able to test physics on a scale, as I'll show you, that we'd never be able to test even at the Large Hadron Collider. Now, if we're looking at galaxies, we're looking back as far as we can see with optical telescopes. But if we want to look back further, it turns out the farthest we can see with light is a time when the universe was 300,000 years old. Because at that moment, the universe was about 3,000 degrees in temperature. And that meant that if you have neutral matter at that temperature or higher, it's not neutral anymore, because protons have captured electrons to be neutral atoms. But at temperatures before that time, it was so hot that the electrons got kicked out. And so instead of neutral matter, you had a charged plasma. And a charged plasma is opaque to radiation. So if we look out at the universe, we keep looking back, we can only see back to a time when the universe was 300,000 years old, because before that it was opaque. Just like if you look at the walls of this room, you can only see to the walls of the room because the walls are opaque. So we've been able to look back to that time, and it turns out the radiation from that time, which was 3,000 degrees then, has cooled down. It's now about 3 degrees above absolute zero, and it's called the cosmic microwave background radiation, discovered by accident in New Jersey, of all places, in 1965 by two astronomers who didn't know what the hell they were doing. But they won the Nobel Prize, because you don't have to know what you're doing to win the Nobel Prize. You just have to do it. But we now have been able to image it, and this is an image of the cosmic microwave background, this surface located about almost 13.8 billion light years away in all directions. It doesn't look like a surface, like a spherical surface, but that's because we projected it on a plane. So I just want to give you an example. So this is a projection. That's upside down. Let me do that right. Okay, because we're in Australia. So that's the projection of the spherical surface of the Earth, and it's the same projection that we've done for the cosmic microwave background. And so let me take this image back. So this is radiation coming at us from all directions. The color represents temperature. The average temperature actually is almost uniform completely to 1 part in almost 100,000. These small deviations in color represent deviations in temperature by less than 1/1000th of a degree. So the universe is the same temperature in all directions up to a part in one part in 100,000. That is also a mystery. We don't understand that. Why? Because these regions could never have communicated to one another at that time, so they shouldn't know about one another, and therefore, how do they know to be at the same temperature? That's a huge mystery, which I'll talk about, something we tried to solve. This line here is the plane of our own Milky Way galaxy. Our Milky Way galaxy is a spiral galaxy, a flat plane. So in this plane, the Milky Way is there, and of course it gets in the way, because lots of stars and dust and everything else get in the way, so we try and get rid of it, which we've done. And see if that works. There we go. This is an image in the microwave background where we've gotten rid of the galaxy. And these are primordial. This is the primordial picture of hot spots and cold spots, regions which were 1 part in 100,000 hotter or 1 part in 100,000 colder. And these were primordial lumps of matter and radiation, which were presumably input at the very beginning of time. And these were the lumps that would later collapse to form all the stars and galaxies and planets and aliens and everything in the universe. The question is, how did they get there? What put them in there? And this is a question we're trying to understand. It turns out we have a theory now that where these things should come from, and it's an amazing theory called inflation. And it says that at the earliest moments of the Big Bang, a billionth of a billionth of a billionth of a billionth of a second after the Big Bang, the universe got stuck in a phase where empty space had an incredible amount of energy. And during that time, the universe expanded very quickly by a huge amount because that energy is gravitationally repulsive. And the universe expanded by a factor of 10 to the 90th. There's not even a word for that. 10 to the 90th in a time scale of a billionth of a billionth of a billionth of a billionth of a second. So it went from smaller than the size of an atom to about the size of a basketball in a billionth of a billionth of a billionth of a billionth of a second. And we have reasons for thinking that's the case based on elementary particle physics. But one of the consequences of that is that originally the universe was microscopic in size and quantum mechanical fluctuations would be important. And it turns out if this picture is right, quantum mechanical fluctuations would get frozen in as the universe expanded, producing density fluctuations which look just like this. That would get frozen in and eventually become fluctuations, real fluctuations in matter and radiation that would form galaxies and clusters of galaxies and everything we see. So if this is really true, you are really here because of quantum mechanics. Because if quantum mechanics didn't work, the universe would have been uniform completely without these little lumps, and without lumps, you can't collapse to form galaxies. So it's really remarkable. This is quantum mechanics in action on the biggest scale you could possibly imagine. Now, this is a nice story. The question is, how can you test this story? Because physics is not just storytelling, that's religion. Physics, and in that case, incorrect stories. But science is about telling stories that you can test, you can make predictions. And so the question is, could we try and understand this? And so I want to show you a little picture because it'll explain to us how we can try and look at this. This is a movie. So this is this moment of inflation, and then the universe becomes 300,000 years old. There's the microwave background, and then galaxies start to form, stars, and then galaxies, and eventually clusters of galaxies. And so we are, today, when we look out at the microwave background, we're looking through those galaxies at the microwave background, which is as far away as we can see. And then the initial time is inflation. So so it'll come back in itself. So this is sort of a brief history of time. Apologies to my friend Stephen Hawking. There's inflation, there's the microwave background, and then everything that happened afterwards. And when we look at galaxies, like the ones I showed you in the Hubble Space Telescope, we're looking that far back. We look at the cosmic microwave background, we're looking that far back. But how can we look all the way back to inflation? And the answer is we discovered, well, there's a way we think we can. But before we do that, I want to explain one of the consequences of inflation, which really bothers a lot of people. If inflation happened, and our universe expanded by a huge amount, it was because energy got stuck in empty space. What happened was something we call a phase transition. A phase transition, like water changing to ice. And if you look at a pane of glass on a cold morning, you'll see lots of icicles in different directions, and so they'll form randomly. And if inflation happened, that means, in fact, our universe isn't unique, because in different regions of space, a phase transition can happen at different times. And that means our region, our microscopic region, could expand very fast and then inflation would end. But somewhere else, the expansion could still be continuing and then it could end later. And somewhere else end later, and somewhere else end later. And in fact, if inflation happened generically, the process of expansion goes out for an infinite amount of time with little seeds forming at different times. And those seeds, each seed is a different universe. And moreover, it turns out when that phase transition completes, there's every reason to think that the laws of physics in each universe are different. Inflation ends in different ways in different universes. And that means there could be a multitude of universes, something we call a multiverse, in each of which the laws of physics are different. In some universes, there could be lots of stars and galaxies. In other universes, not many. Here's another way of thinking about it. This is the multiverse. This would be our universe, which is expanding. And in fact, in between these universes, space is expanding ever faster. So we could never, ever actually see any of these other universes because they're moving away from us far faster than the speed of light. But if this is really true, then it's a little bit depressing because it means it could be that the fundamental laws of nature that govern our universe are an accident. I grew up as a physicist trying to understand why the universe has to be the way it is, which is a noble effort, but it could just be a misplaced effort. It could be, God forbid, that physics is just an environmental science, that it's just an accident. There's no fundamental laws of nature, and our universe, they are what they are, and they allow us to evolve. In other universes, we couldn't evolve. And so maybe if the laws of physics were different, we wouldn't be here to ask the question, which is kind of a cosmic natural selection, relating again to something that Paul may talk about. So this is a picture that bothers a lot of people. It bothers philosophers and it bothers theologians, but we don't care about them. No, we do a little bit, but it bothers physicists too. And the question is, though, this sounds like metaphysics. Because if we talk about other universes we can't see, then, and of course, the theologians it bothers because in some sense the multiverse plays the role of God. It's outside of our universe, it's eternal. And we didn't invent it because we don't like God, although we don't like God, but we proposed it because the laws of physics are driving us to that. But if it's just speculation, then it really isn't different than other kinds of than religion in that sense. The question is, how can we test this weird idea, especially if these other universes are never directly accessible? And I want to show you how we may be on the threshold of doing that. So I'm going to show you, I guess, a little image here which will hypnotize you if it works. There you go. Okay. Stare at that. Now, what this is a representation of something remarkable, something called a gravitational wave. General relativity tells us that matter affects space, that matter curves space. And in fact, every time I wave my hands, which I do a lot, I'm actually disturbing space. And in fact, I'm disturbing space in such a way that when I wave my hands, a disturbance in space goes out through this room, through the rest of the universe, something called a gravitational wave, a wave of space and time. An oscillation in space and time. But gravity is so weak that we can't ever see those disturbances. That's why it sounds so weird. To have a gravitational wave which is big enough to measure, you'd have to move incredible amounts of matter in incredibly violent ways. But if you did, and it's happening right now, right through this room, there are gravitational waves going through you and me, and when a gravitational wave goes through this room, it changes the length of the room. It makes this room smaller in this direction and bigger in that direction, and then back and forth. So if the gravitational wave were coming out of the wall, this is what would be happening to the space in this room. I have a three-dimensional image of it, which is useless but pretty, so I'll show it to you. It's like a snake. Now, gravitational waves have been predicted by Einstein and never measured directly, but we want to detect them. Why? Because if we want to look back to the beginning of time, we can't use light. Because I told you we can only get back as far as 300,000 years. If we want to look back further, we want to use something that can actually make it all the way from the beginning of time to us, that doesn't interact very strongly with all the matter in the region. And gravity is the weakest force in nature. Gravity is so weak that gravitational waves predicted to be, or produced at the very beginning of time, can make it all the way to us. Now, that's a noble effort to try and detect them, which I'll show you about. But we've also tried in the interim to detect gravitational waves, and Australia has been playing a role in this, to detect gravitational waves from other things that we know happen more recently. Say when two stars or two black holes in our galaxy or two neutron stars in our galaxy collide. It's a cataclysmic collision, and it will produce lots of gravitational waves. And we built gravitational wave detectors to try and look for that. I want to show you the biggest gravitational wave detector in the world. As I say, some of the important physics of this is done at various universities in Australia as well. This is the LIGO Observatory, the Large Interferometric Gravitational Wave Observatory. There's two of these. This is in Hanford, Washington. There's another one in Louisiana. And what they are is two long arms, each 3 kilometers long. And if a gravitational wave came down from above, this arm would get a little bit shorter, while this arm was getting a little bit longer. So what's been done is we shoot laser beams down in this direction and this direction, and we bounce them off mirrors at either end, and they come back, and if they're exactly the same length, they come back at the same time. If the length changes, then one laser beam will come back a little bit before the other. It sounds simple. But gravitational waves are so weak, even from colliding neutron stars in our galaxy, that the requirements on this detector are remarkable. In order to detect gravitational waves from colliding black holes in our galaxy, this detector had to be designed, now get this, to be able to detect a change in length of this 3-kilometer long tunnel by a distance equal to 1/100th the size of a proton. You're supposed to go, ooh, 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 yeah. We should. I mean, it's amazing to me that it can be done. And it can be done. And this detector works. Unfortunately, we haven't seen any gravitational waves yet. So it's being built to be better, because that was kind of the edge of the limit of sensitivity, and it's now being improved by a factor of 10 to be able to detect basically 1/1000th the size of a proton change. And it's actually going to come online, and we think we may detect gravitational waves from our galaxy. But a little over a year ago, a different detector claimed to see gravitational waves from the beginning of time. Here it is here. It's at the South Pole. It's a cosmic right-wave background detector. Looking at that cosmic right-wave background, it's called BICEP. It's at the South Pole. Now, the South Pole is cold, but it's not cold enough. So in the summer in the South Pole, we have to send liquid helium over to that experiment because it's not cold enough to be able to get the sensitivity. And as many of you may know, I didn't know this when I first started learning about this many years ago. It amazed me. We can go to the moon. Well, maybe that was faked. We can go the depths of the oceans, but you can't go to the South Pole in the wintertime because no planes fly in or out. And so these are being delivered in the summer, and that's why this is one of my favorite images. This is from the BICEP telescope at sunset, which is an interesting thing because you think about it, sunset happens once each year, and 6 months later, the sun rises. So if you take this picture, you're stuck for 6 months. Which is probably why it was taken by a graduate student. But this detector claimed to see a signal of gravitational waves. Now, where would that come from? So this is just a picture of what happened. Our picture, this was a standard model of the Big Bang before we thought of inflation. But inflation says there's this very short moment when the universe expands by a huge amount when it's very, very young. And when that's happening, matter is moving at an incredible rate. Huge amounts of matter. The entire density mass of our universe is expanding, and that's producing gravitational waves by quantum effects. And we predicted, it's one of the things I did a long time ago actually, predicted that gravitational waves would be produced from inflation. And this is an image from a Scientific American article that I wrote recently. It's very complicated, but since I spent a tremendous amount of time with the artists trying to make sure they didn't get it wrong, I thought I'd show it. Because it gives a little bit of a history. So there's this picture you've seen before of inflation and then up this late time. But inflation produces lots of gravitational waves, and like everything else, as they expand out, they get frozen. Because their period, the time it takes them to oscillate, becomes longer than the age of the universe. And they become frozen until the universe gets old enough again, and then they start to oscillate. So if their period is 1 second, they got to wait till the universe is 1 second old before they start to oscillate. Now, the earliest gravitational waves start to oscillate when the universe is relatively young, but gravitational waves will damp out. So here's a gravitational wave that starts to oscillate early on, it damps out. There are longer wavelength gravitational waves that start to oscillate later, but they die out, other ones later. But then there are gravitational waves with a period of 300,000 years. They just start to oscillate when the cosmic microwave background is formed. What happens then? Well, so here's what happens. I thought I'd show. I was tempted not to show this, but I will. Here's an electron about to scatter radiation for us just at the time the universe becomes neutral. If the universe is the same temperature in all directions, the radiation hitting that electron will be the same in all directions, and it'll scatter it the same in all directions. But if a gravitational wave comes by, the whole universe for that electron becomes smaller in one direction and bigger in another. And that means the universe is hotter in one direction and colder in another, and that means the intensity of radiation in one direction is greater than the other. And what that means is that the electron will scatter radiation and polarize it. It'll be stronger in one direction than another. Those of you who are wearing polarizing glasses know about that, whether you know about it or not. Polarizing glasses work. The reason you use them when you're fishing is that light comes down when it bounces off the surface of water to make a glare. It's polarized. So if the light is oscillating back and forth in this direction and your glasses only allow light that oscillates back and forth in that direction, you don't see the glare. That's why polarized glasses are polarized. But if this is the case, we can look for a polarization signal in the cosmic microwave background. And this is the picture of the microwave background, a small region of it with the hot spots and cold spots. And these lines represent random polarizations, because if it's random, if there are no gravitational waves, it'll just be completely random. This is what it would look like if there were gravitational waves produced at the beginning of time. Doesn't look any different. It's really hard. But the experimenters worked really hard, and BICEP a year ago presented, this was a simulation of what they thought they might see if they could measure polarization in a small region in the microwave background, this kind of snake-like pattern, which is peculiar and unique to gravitational waves. This snake-like pattern is what they predicted they might be able to see. And I think on March 17th, I think a year ago, they published this picture, which could be the most important picture in the history of science, in my opinion. Because if this is really true, they claim to see gravitational waves from the Big Bang. If this is true, it's the first detection of gravitational waves. And these gravitational waves were produced at a time when the universe was a billionth of a billionth of a billionth of a billionth of a second old. And therefore, if it's true, it's pushed our window of the universe back by a factor of 10 to the 49th in time, from 300,000 years to a billionth of a billionth of a billionth of a billionth of a second. It's an amazing result if it's true. They will have allowed us to test our pictures of what happened in the earliest moments of the Big Bang on a scale much bigger, much higher in energy than we could ever test here on Earth. And so people like me were incredibly excited about this, and because it allows us, you see, if it's true, it allows us to test the ideas of inflation, and we can check the theories to see which models work, and if those models invariably produce many different universes. So if we could test inflation, even though we could never directly see those other universes, we could test the model that tells us those universes must exist. We could turn metaphysics into physics. So it was very important. The only problem is it's wrong. Well, it may be wrong. It turns out we've been able to discover, for reasons I don't want to go into, that a signal like this could be produced by dust in our galaxy at the same magnitude of what they saw. The jury's still out, but it isn't obvious that these are gravitational waves from inflation, I'm sad to say. But it means we can build better telescopes and try and look for them, and we're on the cusp of potentially being able to test ideas which were really only vague speculations about the universe at its very beginning. Now, there are other places we can probe for this very early universe. This is a big tank in a mine in Japan with 50,000 tons of water, surrounded by 11,000 phototubes in a Kamioka mine. And it turns out the same kind of physics that might explain inflation predicts, and I'm sorry to say for various people in this audience, that diamonds aren't forever. Because it says that even protons will decay. But happily, they will decay with a lifetime of about 10 to the 35 years, so you don't have to sell your diamonds. But how could we ever tell that? The universe is nowhere near that old. Well, it's probabilistic. The laws of physics are probabilistic. If the average proton takes 10 to the 35 years, if you have 10 to the 35 protons, then one will decay each year. So this detector was built with 50,000 tons of water containing about 10 to the 34 protons, left in the dark, waiting for a proton to decay. Now, none have decayed yet. But again, think about how hard it is to do this, because if the experiment is offline for a minute and that's when the proton decays, you might have to wait another 20 years for it to happen. That's why I'm a theorist and not an experimentalist. But if we saw a proton decay, we could test similar physics. The Large Hadron Collider, which is in CERN, which I would love to talk about at length, and maybe we will. These are the Gothic cathedrals of the 21st century, the most amazing devices we've ever built. But it will test ideas in the next generation, now that it's turned on, that might also tell us about the physics of inflation. Not directly, because if you ever wanted to build an accelerator to probe directly the energy scale associated with inflation, you'd have to build an accelerator whose radius was the Earth-Moon distance. We're not going to do that. But the ideas here might help us point in the right direction. So there's lots of things coming together between the microphysics and the macrophysics that are allowing us to go back to the beginning of time. And we are living at a very fascinating time, the first time in the history of the universe, when we might be able, or at least the history of life on Earth, when we might be able to actually probe directly, essentially, the physics of the Big Bang. But there are all these mysteries. Dark energy, where did it come from? Why is the universe the same in all directions? All sorts of questions. And so even though we're at this fascinating time, we're at this very difficult time because there's so many things we don't understand about this cockamamie universe, which is the universe we see here. And so I want to end a little bit with this, with a quote from a profound philosopher. We'll see if the sound works. I hope the sound works. Okay, so.
Did you know that the Chinese use the same word for crisis as they do for opportunity?
Yes, crisis-tunity.
Okay, I borrowed this from my friend Frank Wilczek. So it says, she says, you know, the Chinese have the same word for crisis and opportunity. He says, yes, crisis-tunity. Well, we are living in a time of crisis-tunity because we have discovered amazing things about the universe that we never would have imagined before, that are perplexing beyond belief, but at the same time, the universe is opening us up to being able to explore those things. So we have crises in our understanding, but we have the opportunity to look out. And that's what makes the present time so exciting. And that's why I'm excited to be a scientist right now. Thank you very much.